Greetings, geologists, and welcome to the Mesozoic era. It's always a favorite of students because this is the time that you learn about dinosaurs. And I want to start off by saying that you're going to have a special lesson after the Triassic period that talks about how do you identify correctly dinosaurs and why are they subdivided the way that they are. You'll only learn about a handful of dinosaurs in this lesson. There are a lot of animals or organisms to address, but there are very few dinosaurs. In reality, there's about probably enough bones that have been discovered of Triassic dinosaurs that you could put them in the back of a pickup truck. Certainly not the case for the rest of the geologic time scale in terms of the Mesozoic era. Another thing that I need to point out is that you need to be correct in your terms with dinosaurs. When we're referring to what you grew up as dinosaurs, that's what we call non-avian dinosaurs. Birds are the remaining dinosaurs. They're related to theropods, and they are avian dinosaurs. So the first half of Triassic is what went on during the Triassic period in terms of plate tectonics, seas, and so forth. And then the second half will get into the life forms. So I want you to look at this photo for a second, and I want you to think about what could have caused this incredibly gorgeous petrified piece of wood to form. This is out of the Petrified Forest in Arizona, which is a national park. This is a very fascinating place. It's in a very desolate Badlands type environment, and you're going to learn a lot about it today. But it's unique in the fact that A, we had the trees available to be petrified, and two, that they were in the correct conditions to have done so. This never would have happened had those trees not been buried in the right depositional environment, which is part of what happened during the Triassic period. So let's get started. What went on with the Triassic period? First of all, it lasted from 251 million years ago to 200 million years ago. It's abbreviated with the capital T and the little r. This is a period of recovery. There are two themes that can go on during the Mesozoic. Diversification after the Permian mass extinction event, the worst of all geologic time, but also the division and split up of Pangaea. Happened in three distinctive stages, and conveniently it kind of happens in order of Triassic, Jurassic, and Cretaceous periods. But you have to imagine at the beginning of the Triassic, continents are all together as one. They're still Pangaea. And during the Triassic, they begin to rift apart. R-I-F-T. Remember that from physical, where we learned about how continental plates pull apart. So MORs, mid-oceanic ridges, create subduction zones by pulling ocean plates apart and squashing them against continents, and rifting are the divergent plate boundaries that tear continents apart. So this was a very important thing to understand because rifting is what would make and change the climate, the ocean circulation, the availability of land mass to live on. So I'll let you in on a secret that when the land masses are all together, the biodiversity plummets. It goes very low because animals are in competition for the same resources. Even though you have a gigantic land mass, you have very little true habitat that's equitable enough and convenient enough for animals to survive in both the plant and animal kingdoms. So when you divide those plates apart, we have rapid diversification, and that's certainly what happens throughout the Mesozoic era, is we see that diversification occur starting in the late Triassic. When we look at the paleogeographic information for the Triassic, a couple of things are to consider. You had uplift during the late Paleozoic of the Appalachians, but really we're not going to see true uplift in terms of plate collisions on that side of the continent for the remainder of the course. That means for the remainder of geologic time that's happened thus far. Doesn't mean it won't be that way in the future. It could certainly become active again somewhere down the line. But the news story is on the Cordilleran Belt, and there's going to be a series of 4 major fluxes of mountain building that occur throughout the Mesozoic and Cenozoic. The The first one of those is going to happen during the Triassic, which we'll get to shortly. So we're going to find that most of the continents exposed because our continent's touching other continents during Pangaea, and so most of it will be interior. It's going to be very desert-like and arid or semi-arid. Along areas where the Arbsaroka Sea still is on the craton, you would have some marine sediments get deposited, which are valuably important for a number of reasons. However, understand that the areas right adjacent to this section are going to have changes in sea level as the Arbsaroka goes up and down. So the Arbsaroka is going to regress farther west during the middle Triassic, and by the end of the Jurassic and early Jurassic, it has completely come off of the continental craton. What we do know is there's an excellent record of Mesozoic and Cenozoic movements of plates. So you might have wondered, how did all these paleogeographic maps get made? How did geologists really know where continents were, what the climate was like, if we can't turn back the clock and go back in geologic time? And that's an excellent question to be thinking. It has to do with magnetic stripes, if you remember that from physical geology. So here's what happens. We know the direction, the orientation, and the order of Pangaea's breakup simply by the direction and movement of continents by looking at mid-oceanic ridge stripes that have been preserved in oceanic rock. We know that Gondwanaland and Laurasia separated during the Triassic, and then we'd see the continents that make up both of those land masses respectively split apart, some in the Triassic, some in the Jurassic, and even some in the Cretaceous. But by the end of the Triassic, a brand new ocean basin had started to form called the Atlantic Ocean Basin. And how did that happen? North America and Africa ripped it apart. And when they did, they began to cause us to have a new ocean basin forming. So this is what's going to happen. These are what magnetic stripes are at the bottom of the ocean. And so you can have normal and reverse polarity. That gives us some valuable information, but it also helps us put a mirror image on either side of the mid-oceanic ridge. So what was stage one of Pangaea breakup? It started with North America pulling apart from Africa, again by rifting. So we're going to get this gigantic magma upwelling event that is actually going to happen from Nova Scotia all the way to North Carolina. So we have a ridge that shows where the North American craton began to separate and also where Africa started to tear off of North America. So the boundaries that we have today of North America are the leftovers of that particular event that happened back in the Triassic. This magma displaced the land, creating lots of fault blocks to occur on the eastern margin of our craton. So when this occurred, that caused a lot of basins to get formed on that side of the continent next to the Appalachians. That area got filled up with a tremendous amount of sediments from the Appalachians as they began to wear down. To be exact, there's around 18,000 feet of them. That's a lot of sediments. That's multiple miles. This is called the Newark Group, and it's famous because it represents where Africa ripped it apart from North America. In addition, there's going to be some active volcanism that will surface that we can actually have proof that this rifting occurred. What is that evidence? Somewhere around 200 million years ago, we have lava events that represent the rifting of North America where this magma upwelled. It would produce multiple flood basalts, sills, and dikes, but the most famous of these outcrops are a series of sills referred to as the Palisades Sill. Very interesting dynamics because you're looking at this large-scale rifting that occurred back at the end of the Triassic, representing the breakup of Pangaea. So when you think about the Palisades Sill along the East Coast, that's the area that I'm wanting you to visualize being torn and being pulled apart at the seams because of this massive magma that had developed under the continents at that time. Starting in the late Triassic and concluding in the early Jurassic, North America and South America ripped it apart. Central America will happen a little bit later. The Tethys Sea began to expand into the Atlantic Ocean basin, and that would allow the Pacific Ocean to invade a new area, an embayment for a better lack of words, what we now call the Gulf of Mexico. That's going to be a puny little small restricted embayment during the Triassic. However, this special place is going to become very important during the Mesozoic because of some evaporites that form there. We would see a climate during the Triassic that's very dry. I mentioned that at the beginning of the lecture. Why is that? Our large Pangaea mass that we have of land, it's far away from any moisture resources unless you're near what's residual of the Arbsoroka transgression. They're large mountains that separate these continents that had collided together to form Pangaea, creating arid intercontinental regions due to rain shadow effect. So our wet climates are going to be the regions near the water bodies, and that's like, well, duh. And then the drier regions should be in the interior. So you'd expect to have more desert-like land conditions right in these sections right here, right where you see the tan areas. One of the things that's important about the Triassic is the presence of red beds and then a number of evaporites that form. This particular picture that you're seeing is the dig site that we go to for Mesalands Community College on our geology field course for MCC. You're looking at real MCC students who are on a dinosaur dig there. And yes, Triassic rocks do have dinosaurs. They're far and few between, but they're very rich in archosaurs, which we'll get to later. Important note is, though, that because of the dry, arid nature, a lot of inland dunes, red beds, and so forth filled and formed in the low latitude and middle latitude regions of North America, South America, and even Africa, indicating that there were very dry desert-like conditions at that time. Other areas would have been near the mountains. They would have had stream beds, which is certainly the case for the area that you're seeing right here in New Mexico. We know that this was a river and lacustrine type environment, so fluvial and lake type stuff. The brand new Gulf of Mexico experienced extensive evaporite deposits that occurred in the late Triassic and early Jurassic, which are going to make up a very important resource that we'll get to when we get to the Jurassic period. But as this separation from South America occurs, North America, that Gulf of Mexico, is going to get dry and wet as sea level rises and falls, and it's going to produce us one of the most magnificent salt domes on the planet. Another thing that you don't really think of, or most people don't think of, in the Triassic period was the presence of coal. But coal is going to form wherever those shallow water bodies would have been along the continental margins or on the craton itself. So you would have found it in some swampy areas, which did exist in small numbers throughout the Triassic period. Nevertheless, the coal reserves are important from any geologic period that we have it. Big news that happens throughout the entire Mesozoic and throughout the first half of the Cenozoic is this brand new plate that we need to have a discussion about, called the Farallon plate. The Farallon plate is probably the equivalent in size, if you're going to compare it to anything modern day, to what the Nazca plate is. So if you'll get out your textbook and you'll look in the plate tectonics chapter and you'll turn to the page that talks about maps, paleo maps, and shows you where the different plates are. There's several of them, but you can turn to the one that actually have rates of movement. It should be towards the back of that chapter for plate tectonics. And as you get there, you're going to notice the Nazca is moving a lot faster than other plates. Now, I'm not suggesting to you the Farallon was moving the same speed that the Nazca is. I'm trying to give you a size representation to look at. Nevertheless, the Farallon is an oceanic plate. So when the Farallon squashes against our continent, it's going to create a subduction zone. Now, the first amount of mountain building we're going to see during the Mesozoic is a unique situation that's created by the Farallon beginning its subduction under our continent, but it's actually bringing in an island arc. The remainder of the three that we'll look at throughout the Mesozoic are the direct result of some unique situations that occurred with the Farallon plate. Ultimately, the end result of the Farallon in the Cenozoic will be to completely subduct under North America and no longer be here. It still has two leftover pieces of which we'll talk about when we get to the Cenozoic era. So that brings me to the Sonoma orogeny. You're going to need to know that this uplifted for the first time during the Triassic. So we know starting in the late Permian, an island arc began to form in the Farallon Ocean Basin, and it formed off the west coast of North America. But by the early Triassic, this island arc had collided. So you have to imagine the Farallon starting to move because of a mid-oceanic ridge between it and the Pacific Plate. And as it begins to push towards North America, this island arc is going to squash against the North American western margin, which I might add looks a lot different in character than it does today. We don't even have all the land mass yet that's going to be considered what we call the western edge of our continent. That's what this whole Mesozoic and Cenozoic Cordilleran orogeny uplift story is all about. So the Sonoma landmass is going to get accreted permanently onto our area of the United States, and it's going to form parts of the states of California and Nevada. It's time that we discuss a little bit about ancient climate, since we talked about magnetic stripes and how we can determine the orientation and movement of plates and the direction and speed of movements of plates. And I didn't mention this at magnetic stripes, so I'll just take a moment to talk about that before we go any further. The wider the strip of a magnetic stripe, the faster the plate movement represents. The smaller that stripe is, the mirror image of that MOR, the shorter the time frame was. So essentially, you had more rapid seafloor spreading when you had a wide mid-oceanic ridge magnetic stripe, and when you have a thin one, you have a less intensive MOR pulling apart. That's important to note. That's one way we can determine speed of plates. Now, how do we figure out ancient climates? That's a completely different ballgame. Geologists are going to use a variety of pieces of information to help piece together a story about ancient climate. We'll look at the annual average temperature for a region that we already know, along with what we call a temperature gradient. We'll talk about what that means in just a second. But if we already know where the ocean basins used to be, and we know where the continents used to be, we can assess some more information by what we know of regions today. A steeper temperature gradient exists where there's a greater temperature difference between polar regions and tropical regions. While that may sound like a no-brainer, you have to think about this for a minute because it gets a little confusing at first hearing of this story. When we have areas that are dominated by primarily continental masses, continents tend to reflect sunlight because they're lighter in color. Their albedo allows for more sunlight to be reflected than is absorbed. So somewhere around the 50%-ish mark is what continents absorb, and then they reflect the remaining amount back to space. If we have any ice coverage, like an ice age going on, that number drops substantially. This is important in understanding how ice ages can last for an extended period of time because the ice itself acts as a reflecting mechanism to reduce the amount of overall solar radiation that the Earth will retain. On the flip side, if you have a dominance of a world ocean, you're going to have a very warm situation because oceans absorb the extraneous heat that comes to Earth. To be exact, they absorb about 90% of solar radiation that they receive. Let me go ahead and throw in another important wahoo moment for oceans. They are storing extra carbon. So we'll have that story a little later on in the Cenozoic. So the way they store that is by building limestone. And limestone is a carbon reservoir. Matter of fact, it's almost an incredible when you learn about just how much carbon the ocean's storing. Eventually that carbon's going to get full and the ocean's going to get to a point where it needs to release that carbon. That's a bad day for planet Earth when it happens, and it won't be the first or the last time it happens when it happens again. Nevertheless, we take these tools for understanding ancient climates because we're going to take the story of where did the plates move based on magnetic stripes and the width of stripes. We're going to add that in with the temperature gradient and come up with computerized modeling that will help us identify what the conditions might have been like in ancient climates. Are we 100% right? Probably not. There's always an error for margin in science, and it's a testing of a hypothesis. That's the beauty of what scientific method is all about, is testing and retesting a hypothesis to see if it was correct. There will be a climate shift during the Triassic period. The global temperature gradient will increase as Pangaea begins to break up during the late Triassic. This will happen as the northern hemisphere begins to move farther north. Why does this happen? Because more ocean basins are going to be present. Even though we had one large ocean during the Permian time frame and early Triassic, as we began to circulate ocean between our continents during the breakup of Pangaea, that will accelerate atmospheric patterns throughout the remainder of the Mesozoic era. So we're in for some interesting stuff that happens, especially at the end of the Jurassic and the end of the Cretaceous. I should take a moment to correlate that to life forms, especially non-avian dinosaurs, because those non-avian dinosaurs, and especially the ones at the end of the Jurassic period, the big giant brachiopods, the big giant sauropods, they had to eat incredible amounts of weight of food a day to sustain their body size and body weight. That food didn't just magically appear. It had to come from vegetation, and the vegetation had to be there because of the right atmospheric conditions. So all of these things are playing a role in putting this dynamic story together about learning of the incredible life forms of the Mesozoic. The Appalachians experienced their last major mountain building event in the Alleghanian orogeny during the Pennsylvanian period. So that means that all throughout the Mesozoic, these mountains are beginning to erode, and they're going to fill up the low-lying basins that are adjacent to it with thousands of feet of sediment as they erode down to a flat plain. So this would occur primarily during the early and middle Triassic, and we still have some of the Appalachians left today, but the ones that you see if you go to the Great Smoky Mountains are really from isostatic rebound and not from true continental uplift because of a plate collision. That brings me to a couple of important rock layers that are noteworthy to discuss about the Triassic period. So we're going to look at a handful of these rocks that were made. They're famous rock layers. Most of these are in the southwest, so they're really not in relationship to the Appalachians. They're more in relationship to the ancestral Rockies and any new mountains that would be uplifted in the Cordilleran Belt. So it's the Colorado Plateau region, and if you're not familiar with that area, it's going to be parts of Utah, Arizona, New Mexico, and Colorado. And it's a section that the Grand Canyon kind of sits smack dab in the middle of. Well, the Moenkopi is a famous rock layer from the early Triassic, and it's important that you know as a geologist at what part of these periods these rock layers were deposited. That's good test question stuff right there. And why is that important? Because the depositional environment changes throughout these periods. Certainly the case in the Triassic. What is this rock layer famous for? This is the rock layer right in here. Notice that it looks like a brick red color or a deep chocolate color, and that's the common characteristic color of the Moenkopi. Moenkopi is made up of mudstones and sandstones that are full of ripple marks, and that would indicate to us that these were nearshore environments that were close to the advance and regression of the Arb-Soroka Sea. Important to note that there's a number of trace fossils found in the Moenkopi of even early reptiles and amphibians, and even a handful of our early dinosaurs that existed during the Triassic. This is a classic ripple mark, and it is a Moenkopi siltstone. So if you've taken physical at MCC in a face-to-face class, you've likely seen this specimen. So the specimen actually came from Arizona, legally collected, I might add, but nevertheless, it's classic Moenkopi color, it's the right age, it came from a geologic formation in that Arizona region that's famous for having Moenkopi deposits. Now, the next layer is kind of interesting. It's called the Shinarump. It's a conglomeratic rock layer. This is unconformably directly on top of the Moenkopi. What does that mean? It means that we have an early Triassic rock deposit, which is the Moenkopi, and directly above it, we have a late Triassic rock layer called the Shinarump. The Shinarump represents river or fluvial deposits. That should not be a surprise. And these braided streams that created these river deposits were constantly being reworked as we would have rivers that would flow at high peak capacity and then at regular flow. So you would have sheets of sands, then you would have interbedded lenses of gravels within more sands and gravels. The end result was a very interesting layer of the Shinarump that sits on top of the Moenkopi. Another beneficial thing about the Shinarump is that it contains uranium. So uranium is useful to us in terms of reclamation of an ore. So these sandstones contain some uranium fossil deposits of ore that we use for economic gain. Now, my personal favorite of all the Triassic rock layers is the Chenley, but the Chenley has a lot of members. And I can tell you from the digging that we do in Tucumcari, New Mexico, the Redonda Formation, which is famous for containing archosaur fossils, is also one of the members of the Chenley. So we're going to look at a number of the members of the Chenley from the Petrified Forest today and limit it at that because we could spend an entire semester just doing a case study over the Chenley. So what is so famous about the Chenley? First and foremost, it's a colorful layered rock. You'll see another one that looks just like it in the Jurassic called the Morrison Formation. Don't confuse the two. They're from two very different time periods. One's from late Triassic, one's from late Jurassic. Nevertheless, the Chenley was deposited as shales, siltstones, and sandstones from the late Triassic, and I might add they are very, very rich in bentonite. Why is that significant? Bentonite comes from volcanic ashes, so I need to just point out, you just learned about the Sonoma orogeny, right? So these volcanic arc islands are going to accrete onto our continent, and as that subducting plate of the Farallon begins its descent, it's going to fuel up island arcs that are now volcanic volcanic systems, just like Mount St. Helens. So now we're going to get a string of volcanoes along that border in New Mexico or along that border in Nevada and California that's going to produce some pretty impressive eruptions that are going to help bury these magnificent trees that existed during the late Triassic in Arizona. So if you've not been to the Petrified Forest, it's kind of on the eastern side of Arizona, and it's a remarkable place because this is the landscape, and you're like, really? There are petrified trees out there? There really are. It looks like badlands, and that's the characteristic look of something called a badlands. So you might hear the term badlands applied to many areas across the world, and it simply is a barren landscape that has very little plant life. Nevertheless, the Chenley is a remarkable piece of evidence that Arizona didn't always look like this. So I'm going to give you an image in just a few minutes to pull from that will help you understand the significance of what Chenley used to be and what it is today. It was created by river systems, deltaic systems, and even lacustrine or lake environments. There are many members that make it up, and each one has its own special personality. So we're going to look at the Petrified Forest as a case study. And I'm going to kind of walk you through some of the highlights of the park and talk about the different formations. This is a famous area inside the park called the teepees, and it's because they look like teepees. Now, this is the oldest rock layer of the entire system that you'll see, and it's called the Mesa Redondo member. And this member is very unique because it has yellow, it has red and purple rock layers. This is a floodplain deposit, and that floodplain deposit would have been right near the adjacent sandstone channels that were being deposited by the Shinarump member. The next member that you would see in the petrified forest is a really beautiful rock layer, and it's called the Blue Mesa member. This is going to have the purples, the greens, the grays, the blues. These are all mudstones and shales. It's a pretty soft layer that makes up these slopes that you'll see throughout the park. Above the Blue Mesa member, you'll see the Sonsella member. And that actually is subdivided again into 3 layers. But as a unit, I think we can talk about the significance that they are cross-bedded sandstones. That's the only one that's like that. So it's got cross-beds and conglomerates, which indicates 2 types of things. And the cross-beds are not substantial high angle, so that might suggest to you fluvial deposits, and the conglomerates is the other clue. So as the conglomerates are deposited during high flood conditions, regular fluvial crossbeds, which are low-angle crossbeds, get deposited for the residual portion of it. The petrified forest member is by far the most famous because this is the one that contains a bulk of the petrified wood that you'll find in the petrified forest. As an FYI, it's illegal to collect petrified wood in the park, and most people know that, but it's actually a crime. And so it's kind of a big deal, and I can tell you, having taken a lot of groups there now for field course, I think most people obey the law. But every little piece matters. So the petrified forest, when you drive through the areas with the log, you'll notice that it kind of has a rusty reddish mudstone that you're walking on as where the trees are deposited, with a brown sandstone layer that kind of crops out at different places throughout the area. That would be the petrified forest member. This wood represents some incredible trees, and that's the story that we need to revisit. This is the image I want you to have of Arizona, not the image you have today, is it? If you think about Arizona, this is not what it looks like. Now, there's actually some areas of Arizona that have mountains that are alpine, like if you go out near Flagstaff, that area is beautiful with mountain ranges. Even as you get up towards the Grand Canyon, the rims are more mountainous. If you go to the North Rim, it sits over 9,000 feet in elevation, so it's pure alpine. But if you go to somewhere like the petrified forest today, it looks like the Badlands I just showed you. Does not look like this. But this is the image you need to have that existed back in the late Triassic. So we had the dominant type of land plant that was in existence in this area along these river systems would have been conifer trees and ferns, but conifers making up the trees that we're going to find buried in the petrified forest. How did they get petrified? That's a story in itself. These logs got washed down rivers, probably at high flow times during river systems, and they got buried very quick. And the quick story is probably from volcanic eruptions and flooding, maybe even lahars, who knows. But we do know that the rock layer that they're buried in is rich in bentonite, and that bentonite plays several different important roles. The bentonite's going to have a high silica concentration, and the silica becomes instrumental in providing the silica necessary to permeabilize the logs, which will ultimately cause petrification. Second of all, the volcanic ash and the bentonite itself today is important because it shrinks and swells. And as it shrinks and swells, it allows for new logs to be discovered and exposed. So it's kind of an important element for how we find petrified wood in the Arizona desert or anywhere that has this type of system. So you don't just have to find petrified wood in the petrified forest. There's actually some areas that it exists in the Chinle that is public lands. And not all of it is beautiful and red like this. A lot of it's white and very non-permeabilized. So the depositional environment dictates everything for the petrified wood that you find anywhere across the world. So the silica from the volcanic ash, along with other minerals in groundwater, gets absorbed into the actual ancient wood, the tree itself, and then it crystallizes throughout the cellular structure. That's what's so magnificent. So no two pieces of petrified wood will ever be identical. This is a gorgeous piece from the petrified forest, and look at the numerous colors that you can see. In this particular piece, you can see clear quartz, purple amethyst, which is a form of quartz, yellow citrine, smoky quartz, and many other minerals that are present there. So this is rock solid. Something like this that was sold at a table, or should I say as a table, even this log, which you're looking at a stump here, and I'd say the stump is a good 4 feet wide. This would probably run anywhere from $25,000 to $40,000 or $50,000 polished and ready to go. And there are some private landowners that didn't get their land domained, or meaning eminent domain, when the park took over the land, and they actually sell some of this stuff and ship it worldwide. Acaroloxium arizonicum is the primary species of wood that you'll find throughout the park. So there's 3 major types of trees that are found there, but one's dominant, and 2 other portions of trees that are found are in very small quantities. But that's not all the plant story that's in the petrified forest. We find up to 200 species, different ones of plants and trees that lived throughout the late Triassic landscape. So you have to go back and think about that image that I showed you of that remarkable landscape and understand it was a thriving forest back then in the late Triassic, not a desolate desert like it is today. Now, this is a remarkable thing that people, when they visit the park, almost find too good to be true. Looks like someone took a chainsaw and just cut these things into small log segments. That is exactly not what happened. Here's what happens. The trees were laid down in a horizontal layer, the law of original horizontality. Later on, they're going to get buried with more sediments above them, and then as the Colorado Plateau uplifts, it's going to put strain on the earth from below. And as it does, it fractures along a clean quartz break, and it's going to break along tree rings is what's going to happen. And so that's why it looks the way it does. Nobody's gone out there and cut these things. You would need a diamond grade saw to do that. Now you can cut petrified wood, but you're going to have the right goods to do it. But everywhere you go throughout the park, you'll see the same phenomenon. It's really kind of eerie when you first see it, because you're like, that is so strange. But it's just the natural way that the quartz actually breaks apart, where it fractures. So it's a unique type of fracturing where these quartz crystals break apart in a more clean, even surface as opposed to something like a concordial fracture. When we look at the petrified forest and you see this remarkable set of trees, you begin to get it that the landscape was different in the late Triassic and that it's changed today. It'll change again in the geologic future. So from now on, after you've taken this class, everywhere you go, that's the kind of mindset I want you to have. What did this place used to be like? I wonder what it's going to be like in the future. You have to ask yourself those questions, especially when you pick up rocks and fossils and you look at the landscape, because you begin to realize there's always a story, and the stories can be pretty magnificent, like the petrified forest. There's still one more rock layer to discuss about the petrified forest that's late Triassic in age, and it's the Owl Rock member. This is the youngest member of the late Triassic Chinle, and it's made up of a pinkish orange mudstone, and it even has some lenses of limestone indicating where the Arbsoroka Sea came in and out of the area. It also indicates evaporating inland lakes that would have been adjacent to the shoreline. Now, what's really crazy about this formation is what sits directly above it and the amount of missing time that's there. This particular rock layer is overlain by the Bidahoochee, and this formation, isn't that a fun name, Bidahoochee? Well, the Bidahoochee is late Cenozoic in age, to be exact, 8 million years old. That means there's a missing gap of 192 million years. Now, what I'm pointing to in that photograph is really important because that is going to represent pillow basalts. I'm not kidding. So we were on field course a few years ago, and a retired park ranger came to visit with us. He was so excited that we were there. You could see we were having our lessons about the petrified forest, and he said, "Come here, do you want to see something really cool?" And I'm like, "Well, sure, please show me." And he walked around to the back of this place that's in the park, and it used to be a lodge. So if you go there, you'll know what I'm talking about. You'll have to go to the kind of the left side of the lodge. And as we walked back there, it was really quite fascinating. I right away knew. I was like, oh my gosh, these are pillow basalts. That's so cool. So from physical geology, you should remember that pillow basalts represent ancient volcanic island arcs. It's kind of in tune with what we're seeing here, but keep in mind this is Cenozoic in age. Something completely different than where we are right now. So we'll be getting to that later. Nevertheless, these pillow basalts are there and they're very young. So in this picture, that's Colin Kubachov. And he has gone with this multiple years on field course and even as a sponsor. So I can tell you that all of us were pretty stoked by seeing these pillow basalts, but understand they represent a completely different geologic story. Again, every place has a whole storybook of chapters to interpret, and the Baidahuchi is just one of those stories of the entire petrified forest. Another really cool thing to see is this. If you go to the Petrified Forest, I recommend to stop at Newspaper Rock. It's clearly delineated on your map, so you can stop. It's not something you can hike down to, so you'll have to have a pretty good zoom lens to see it, but the Native Americans drew on these rocks, and they would have been drawing on areas that had thick accumulations of manganese oxides, otherwise known as desert varnish. And these are very real petroglyphs. So it's kind of a neat thing to see and understand how geology actually does work and people use it for the greater good. As we leave the petrified forest, I'll tell you a quick story because this was one that happened to us the first year of field course. What you're looking at is the beginning of a tornadic storm. The storm had followed us all day long. We had already been to Meteor Crater, and they had to cut our tour short because of lightning and high winds that came up that were about 60 miles an hour. And we left and headed towards the petrified forest, and as we did, we were about 3/4 of the way through the park, and the storm began to blow in. It had been a great distance away from us. At least it looked that way, a good 50 miles away. And it came up so quick. We were all hiking one of the trails, and we had to make a beeline for it with horizontal rain, wind gusts well over 50 miles an hour, and that quartz sand that had eroded down from these quartz-based petrified logs was just killing our eyes. Understand it was cloudy, so most of us didn't have sunshades on. And so we had to just like run for it and hold our eyes shut or cover them. I can remember running like this, just kind of holding my hands over my eyes, thinking, I'm never going to make it. We're never going to make it. It's just raining and it's starting to flash flood and we're already in transit. And this is as the storm begins to hit. This road right here that you see got completely covered within a couple of minutes, less than 5 minutes. You couldn't see the road. So we had made it to the other side of the park, the far west side of the park, which is about a 20-mile drive to the nearest city called Holbrook, Arizona. Water filled the streets of Holbrook up to past the tires of our vans and Suburbans. So that's how much rain fell that quickly. In the desert, that's a real testimony, especially in lands like this where there's bad land topography. There's nowhere for that water to go. It's not going to seep in very well. It's going to run off because of desert pavement. So the petrified forest can be a very dangerous place during monsoon season. And of course, we were there in monsoon season, which is late July and early August. So something to think about as you travel throughout desert systems and certainly the Southwest is to remember that weather can be a rather dangerous thing. I might correlate that to historical geology by saying these same kinds of weather patterns would have been important for how life forms reacted, what kind of life forms could existed, how they got buried. On a final note, I might link it to our course by saying after one of these storms would be a great time to find brand new fossils anywhere in any type of situation, whether it's right where you live or in the middle of the petrified forest. But remember, if you're in the petrified forest, it's illegal to collect. That will bring us to taking a break. We'll come back and learn about the life forms of the Triassic. See you back after the break. Bye.